In a previous video, we learned about how to use the Laplace transform equation to essentially derive frequency domain functions giving a initial time domain function. So now this function here, x of t is equal to e to the negative at cosine omega t, that's actually a very common transformation that we'll make, especially when solving ODEs and using the completing the square method. So I thought this would be a handy video because it'd be a little bit more complex of a derivation, but then it'd also be handy to see the background behind it because we're going to use it so much. So now, similar to the previous example that we learned before, we can start out with our frequency domain function, capital X of s, and that is going to be equal to 0 to infinity of x of t, or e to the negative at cosine of omega t, and this is all going to be multiplied by e to the negative st dt. Now this can be simplified as integral going from 0 to infinity of e to the negative a plus s times t cosine of omega t dt. So now the easiest way to solve this problem would be integration by parts. So let's start setting that up. So we can let u be equal to e to the negative a plus s times t, such that then du will be negative a plus s times e to the negative a plus s t dt. Then dv would be the remainder of our equation, or essentially just cosine of omega t dt. And if we integrate that, we get v is equal to 1 over omega sine of omega t. Now, the next step is we have to essentially multiply our u and our v together, and then we have to essentially evaluate it going from 0 to infinity. So let's do that. So we'll have 1 over omega sine omega t, and then e to the negative a plus s times t, evaluated from 0 to infinity. Now the next step is we're going to subtract the integral going from 0 to infinity, and we're going to multiply du and v. So we're just walking through our integration by parts steps. So notice this negative out front here, so that'll make this negative positive, and we'll have a plus s e to the negative a plus s times t, and then we can divide by omega, and then multiply by sine of omega t dt. Now, real quick, if we were to look at this right here, so if we were to evaluate at infinity, so we essentially have 1 over omega sine of omega times infinity, and then e to the essentially negative infinity, because we'll have negative a plus s times t, so t will go to infinity. So this will actually be 0. And then the second part will do minus, and then we'll evaluate when it's 0 instead, which in this case we'll have 1 over omega sine of 0 e to the 0, which in this case is also 0. So we can essentially just say that this entire term is equal to 0. So then we're just left with this term right here. So now what we can do is we can actually use integration by parts yet again. Now we only have a total of 2 times, so this is the last time, promise. So we can set u this time equal to a plus s divided by omega e to the negative a plus s times t. So then du will be equal to negative a plus s squared divided by omega times e to the negative a plus s times t. Then we can say dv is going to be equal to sine of omega t dt. And then by integrating, you get that v is going to be negative 1 over omega cosine of omega t. So now, what we can do is we can pretty much do the same thing. So we can multiply our u and our v together, and then evaluate going from 0 to infinity. So in this case, we'll have negative a plus s divided by omega squared times cosine of omega t e to the negative a plus s times t, evaluated from 0 to infinity. And this time, this term will not equal 0. So that'll come in handy later. So then we'll have minus, and then now we're going to be multiplying our du and our v. So notice we have negative, negative, so those are going to cancel and be positive. So we'll essentially have negative, and we can pull out our constants. We'll have this a plus s squared divided by omega squared. And then we'll integrate going from 0 to infinity of e to the negative a plus s times t, and then cosine of omega t dt. Now notice that this part right here looks awfully familiar, because that's pretty much what we started out with from the beginning. So we could actually say, let me get a different color here, we could say that our integral going from 0 to infinity of e to the negative a plus s times t cosine of omega t dt is equal to negative a plus s divided by omega squared cosine of omega t e to the negative a plus s times t, evaluated from 0 to infinity, minus a plus s squared divided by omega squared, going from 0 to infinity, e to the negative a plus s d, cosine of omega t dt. So we can essentially add this term off to the left-hand side here. So let's do that. So then we'll get, in parentheses, we'll have 1 plus a plus s squared divided by omega squared, integral going from 0 to infinity, e to the negative a plus s times t, cosine of omega t dt, where this 1 here is coming from this term, and this a plus s squared divided by omega squared is coming from this term. And then that's going to be set equal to negative a plus s divided by omega squared times cosine of omega t e to the negative a plus s times t, going from 0 to infinity. So now what we can do is we can evaluate this right-hand term first. So that is going to actually come out to be a plus s divided by omega squared. And the reason for this is the first part is infinity. So again, we'll get this e to the negative infinity, which is equal to 1 over e to the infinity, which is 0. And then for the second part, we'll subtract and then evaluate when t is equal to 0. So we'll have e to the 0, which is just 1, and then cosine of omega times 0, or just cosine of 0, which is going to be equal to 1. So then that just leaves us with a plus s divided by omega squared. So now, what we can do is we can then multiply this constant here over to the right-hand side, such that we'll get the integral going from 0 to infinity, e to the negative a plus s t cosine of omega t dt is going to be equal to a plus s divided by omega squared, and then we'll do 1 divided by 1 plus a plus s squared divided by omega squared, which will be equal to, almost there, home stretch. So we'll have omega squared plus a plus s squared. And that's it. So now we know that the Laplace transform of e to the negative at cos omega t is going to be equal to s plus a divided by s plus a squared plus omega squared. And that's it.